Hi everyone. So in this video, I'm going to be covering section 2.4 and 2.5. And this is on the exactness, exact differential equation. And a lot of these methods are really developed through a process called reverse engineering. So what reverse engineering is just that you start with the solution, and then you see what kind of a differential equation that will come from the solution. So here we're going to look at something that's called a level curve from multivariable. So if I take this function that is in two variable x and y, and I set that to equal to a constant, and if I differentiate this, what would the differential look like? Well, if I differentiate the left side and I differentiate the right side, if you differentiate a constant, that's a 0. If you differentiate the left side by chain rule, you're going to get the derivative of f with respect to x first. But this here could be a chain rule. I'm not saying I'm differentiating with respect to x or y. So this is a general differential. It's just a d. So here you have to consider the fact that x can be a function of wherever we're differentiating with respect to. So here you have to differentiate f with respect to x first, but by chain rule I have to now multiply by the derivative of x, okay? And since this is a function in two variables, there's partial derivative. So now you have to take the derivative of f with respect to y, and then by chain rule you have to multiply by the differential of y. So this is something you've learned in multivariable, and this is what you'll get as a differential equation. Okay. So now anytime I have something in this form, I know exactly what my solution is. It's going to be this guy. The problem is, how do I get back to capital F given f of capital f of x and f of y? So f of x just simply means that you're differentiating f with respect to x. F of y simply means you're differentiating f with respect to y. And that's really it. That is 2.4. Now, they're not going to label this as f sub x or the df dx. They're going to give it a different name. So when they give you a differential equation in this exactness form, they use m to refer to f sub x, and they use n. The reason for this is you can't just assume that m is the differential of f with respect to x, and n is the differential of f with respect to y. So it's really a question mark. Is this really the derivative of f with respect to x? And is this really the derivative of f with respect to y? So this is given to you as a problem, and we really have to confirm the fact that m is df dx, n is df dy, and if it is, then it is exact, and here's our solution. And it's equal to some sort of a c. Okay? Okay, well, how do I check? Well, from multivariable, if I differentiate x first and then y, it is equal to differentiating y first and then x. So the order does not matter. And if I can somehow check that indeed f of xy is equal to f of yx, then that means that this is true. So if I can somehow check that m, if I differentiate this with respect to y, and I take n and I differentiate this with respect to x, then what we've shown is that indeed m is going to be the derivative of f with respect to x, and n is the derivative of f with respect to y for some f of xy. And now our goal is to really find this guy. Okay? Well, how do you get back f? Well, there's two ways. If I know that m is the derivative of f with respect to x, here we've checked it as exact, then I'm going to take the antiderivative with respect to x, and you'll get back f of xy. You get back f of xy also by taking the antiderivative of n, because here, once we confirm that n is indeed the derivative of f with respect to y, we can take the antiderivative of that with respect to y and get back your capital F. And this will allow us to combine both pieces together to really get our capital F of xy. And our final solution, the general solution of this guy, would be of this form. Okay? Okay, so let's do an example. And then I'll explain 2.5, which is an extension of this method. Okay, so it's very easy to create a differential equation coming from a level curve. You just start with the level curve itself. So let's say here's my level curve. And I'll introduce a third term. I'll use y to the third. And let's say it is equal to 7. Let me make this 8. Okay, so you'll see that when x is 0, what do we get? We get this to be 0. That's a 1. Let me make this a 9, just so that it'll just come out to be a very nice number. Okay, so when x is 0, y is 2. Would that make this true? So that's 0. This would make it a 1. When y is 2, that's an 8. So 1 plus 8 is a 9. Okay? So if I were to differentiate this, just take the differential of the left, take the differential of the right, we'll get ourselves the differential equation, and that will be the start of the problem. Here, I'm just giving you the solution to begin with, and then you can kind of see the whole process, okay? So if I differentiate the right side, it's a 0. If I differentiate the left side, you have to differentiate this with respect to x and then with respect to y. So let me do it term by term. So if I differentiate this first one, it'll be a product rule. So it'll be the differential of x, but then you keep the second guy. And now I'm going to keep the first one, which is x. I'm going to differentiate the y squared, but that will be 2y multiplied by the differential of y. For the next one, oh, that's a y on top. So e to the xy. They're both at the exponent of e. So if I differentiate this one with respect to, well, e to the xy is just e to the xy. But I have to differentiate the e to the xy, so d of xy, and I'll do that in my next step. And I'm going to differentiate this third guy, which is going to be 3y squared dy. Okay, so this whole thing is equal to 0. Y squared dx plus 2xy dy. And if I differentiate the product, you differentiate one, keep the second one. So if I keep x, you differentiate y. If I keep y, you differentiate x. And then you have 3y squared dy is equal to 0, right? And I'm going to group all my dx and group all my dy. So here's my dx. Here's another dx. And then the remaining would just be all dy. So my dx, if I group all my dx together, you have a y squared, and that's going to be a y e to the xy. If I group all my dy together, here's a dy term. Here's another dy term that's going to be multiplied by e to the xy. And then here's another dy term. So in total, you have 2xy plus 3y squared plus x e to the xy. Okay? And that's equal to 0. Okay, so this is a problem that's going to be given to you. And you're simply asked to solve. And this was engineered so that it is an exact differential equation, because we started with a level curve, we differentiated it, and here we are. So all I have to do is make sure that this is indeed the f sub y, this is indeed the f, this is the f sub x, and this is the f sub y, and we're going to integrate both each one to figure out our f, and get back the original differential equation given this initial value. Okay, so let's begin. So this is going to be our m, this is going to be our n, and in order to check if it's exact, I'm going to differentiate this with respect to y, because I'm assuming that if this is indeed coming from the same f, and this is f sub x, this is f sub y coming from the same f, then if I differentiate this now with respect to y, differentiate this with respect to x, they should be the same. Okay? All right, so I'm going to differentiate this with respect to y. I get 2y plus, and here I have to apply product rule. So I'm going to differentiate y, which will give me y, and keep the e to the xy. Plus, now I'm going to keep my y and differentiate e to the xy with respect to y. Well, that'll be e to the xy. Chain rule tells me I have to multiply by the derivative of this with respect to y, and that'll be x. Now I'm going to differentiate x, n with respect to x. So if I differentiate this with respect to x, well, the derivative of 2xy with respect to x will be 2y. If I differentiate this guy with respect to x, well, relative to x, that's a constant, so that's a 0. It's going to go away. Now I'm going to differentiate this with respect to x. So that's a product rule. I'm going to differentiate the first guy, so that's x. Take the derivative of x with respect to x, you get a 1. So that's e to the xy plus. Now I'm going to keep that x, and I'm going to differentiate this e to the xy with respect to x. So by chain rule, if I differentiate xy with respect to x, you get a y. And if you compare both, they are exactly the same. And this confirms that they're coming from really the same f. So this is going to confirm that this is indeed the derivative of capital F with respect to x, and this is indeed capital F with respect to y. So they are indeed exact. And now the solution will be this f of xy is equal to c. But what is f of xy? Well, we're going to integrate this with respect to x because this is f sub x. We're going to integrate this with respect to y because this is f of y, and it'll give us the same f. Okay? All right, so my f of xy is the integral of y squared plus y e to the xy, and this is with respect to x. Okay, but we can also get the same guy, the f of xy, by integrating the f of y with respect to y, and that is the 2xy plus 3y squared plus x e to the xy. Okay, so I'm going to integrate this with respect to x. So y squared is a constant relative to x, and it'll just be y squared x. If I integrate this guy with respect to x, I see here that this is a chain rule. And so to undo the chain rule, you just get back this, e to the xy. Now there is a constant, but it's a constant relative to x. So this constant can actually be a function in terms of y. So it's not really a constant, it's a function in terms of y. But relative to x, this is a constant. And we're going to have to figure out what this guy is. I'm going to integrate this with respect to y. And so the antiderivative of y is really y squared divided by 2. This 2x in front is a constant relative to y. So you get x, y squared. The antiderivative of this with respect to y is y to the third. And this is really a chain rule that happened. So when I take the antiderivative with respect to y, you get just e to the xy. And then here you get a constant relative to y, so this constant can actually be a function in terms of x. Okay, so this is really your solution here, the f of xy. All we're missing is this c of y, which means if I can figure out the term that contains purely in terms of y, we're done. Well, we're going to look at the other solution to help us figure out what the c of y is. Well, it's not the first guy because there's an x. It's not the third guy because there's an x. And it's not the last guy because there could be an x in there. What we're looking for is the term that contains just y. And this is it. It's going to be that y to the third. So this is our c of y. So what's my f of x? Y, it's going to be xy squared plus e to the xy plus y to the third. And so here's my solution. it's equal to some sort of a constant c. Now this is a general solution. But we know that when x is 0, my y is a 2. So I can plug that right in to get that my c must be a 9. So now my particular solution is this. That's exactly what we started with. Okay. So that's really how a lot of these older methods work. That you start with a solution and you kind of ask yourself, if I differentiate this, what kind of differential equation do I get, and how do I undo that? How do I get back to that original equation, right? Okay. So it's not a very satisfying method, and it only works under a very certain condition, and it's exactly this. It needs to be exact. Okay. All right, so I'm going to do a second video. I'll stop here. I don't want to make the video too long. So I'll see you guys in the next video when I cover section 2.5.